All right, here we go. So today's a very important day. We've had a couple of those big moments in calculus. Chain rule was a day like that. I don't remember if we had any. Chain rule was a big one. Maybe when we first learned how to do a non-limit derivative. Those are kind of momentous days. This is another one like that. This is a big one. This is very good stuff. So I'm gonna teach you guys about how to do implicit differentiation. So to differentiate implicitly. This is a huge topic in calculus. It makes things much easier. Sometimes it unlocks problems that we otherwise couldn't do. But to understand this, we have to know the difference between what we mean by implicit and explicit in math. So an explicit function is one where the dependent variable, usually be y or f of x, is written strictly in terms of the independent variable. So y is by itself equal to some function of x. That's what we're used to, right? I can't remember, I can't think of many instances where we haven't had those types of functions in the past. We've very rarely dealt with anything other than that. We will today though. So the y is isolated. In an implicit function or an implicit equation, the output variable is not isolated and it frequently appears in multiple terms and mixed in with other variables. Okay, makes things much more complicated. So for example, let's just practice a little bit to kind of warm up to this lesson. So if we want to take this derivative, if y equals x squared, this is easy. What is dy dx? 2x, right? And technically, it's 2x times dx dx, which is just 1, right? We don't write that part. But we've got two layers to this, really. We've got an x squared, we got a hand squared, and then inside the hand we have an x, but the derivative of x is 1, so we just always ignore that. We think of this as a single layer function, right? But give me thumbs on that. Does that make sense? Everybody understand where I'm going with that? Okay, so it technically, we treat this as a single layer function because the inside layer is so trivial. Right, we're differentiating with respect to x. The derivative of x with respect to x is 1, right? So we don't bother. We just get 2x. But when we're differentiating with respect to a different variable, okay, well, then we're not differentiating with respect to x or y. We're differentiating with respect to t. So we have to take that additional step. In fact, if we had done this previous problem as easy as it looks, let's just take this one. What if we had instead calculated if y equals x squared and we calculate dy dt? Well, how are we going to do that? Well, what's the derivative of x squared? What's the derivative of hand squared? 2 hand, right? So the first step looks exactly the same, right? Notice those are the same, but the second step is going to be a little different. Now that we peek inside, what's the derivative of x with respect to t? Dx dt, right? You see the difference here. Because we're differentiating with respect to a variable other than x, the second layer doesn't just go away. We're stuck with dx dt. Okay? So what about this bottom one then? What's the derivative of z with respect to t? Well, at the outermost level, it looks like we've got a product here, don't we? Right? So we've got to apply a product rule here. But I agree, I've got a product of x and y squared. Okay? So help me out. What am I going to do? What do I got? I got to do, okay, so I'm doing x times the derivative of y squared first, right? V prime, call it. If u is x and v is y squared, I get x times the derivative of y squared, which is what? Okay, but am I differentiating with respect to y? No, I'm differentiating with respect to t, right? So what's the derivative of y squared with respect to t? This is a chain rule issue. That's all this is chain rule. I've got two layers now, right? I've got two layers here because the variable does not match up with the variable of differentiation, right? This thing on the bottom, oftentimes we call this the variable of differentiation. It's just what we're differentiating with respect to, right? Yikes, differentiating with respect to. Now, I hate to say that because that's a dangling participle. You know, I'm kind of a grammar Nazi a little bit. I should say to which I am differentiating, right, or something. But you get the point, right? So forgive my grammatical slip there. That's the variable of differentiation. So when they're the same, I don't have that second layer, right? But when they're different, I need that second layer in my function, like we had here, right? This is a single layer function in the first case, but here, because I'm differentiating with respect to t, I've got two layers. I've got the squared layer, and then I've got the derivative layer, because the derivative stays around. It doesn't go away like it did here. Okay, give me thumbs on that. I got to know where we are. Okay, so this will kind of help us out then. Okay, if you're not sure, see if you can articulate a question, because it helps you and it helps me. You see the difference between these two things. The difference is this. That's the difference. Dx versus dt, right? Well, because that's what I'm trying to find. I want to find in this case, because I'm choosing to differentiate with respect to t, right? For example, maybe what could this mean? Okay, this could mean, like, if we're looking at projectile motion in physics, if y represents the vertical position of an object and x represents the horizontal position, well, then we know that the vertical position is related to the horizontal position in this way. Whatever the horizontal position is, the vertical position is going to be that squared, right? So if we look from the side, the trajectory this thing's going to describe is going to be parabolic. Okay, but if this is happening, if the object is moving along that parabolic trajectory in time, right? It's actually an object that's physically moving along that trajectory. Maybe I want to know, okay, well, what is the rate of change of the vertical position of the object? Okay, in other words, what's its vertical velocity? Just the vertical component of velocity. Well, then I'm going to find dy dt. What's my answer? The answer is the vertical speed of the object is equal to 2 times the horizontal position times the horizontal speed, dx dt. Okay, I don't expect you to understand all that physics stuff, but I just wanted to give you a context for why. The question was, why am I differentiating with respect to t? Because I want to know, right? Because I want to know what dy dt is. Right? So there is a context where I might want to know that. So I'm differentiating with respect to a variable that doesn't even show up in the function. Right? But that's okay. That's okay to do.
How do you multiply it by dx dt if dx dt we don't know what that is?
Well, because presumably maybe we might know what it is. Maybe we have some initial conditions where we could plug that in. Okay? Like it's yeah, I mean that is the relationship. This is the mathematical relationship. Whether or not we're able to use it depends on what we know, right? We're going to do some problems in your fairly near future where we're going to be solving for like we'll be given some initial conditions and we've got to go back and figure out what values, plugging those initial conditions in to figure out what the value of this quantity is that we just derived. Okay. But the point here is, like, I can differentiate these two variables with respect to a different variable. That's fine. Okay, that's fine. I just end up with something that's a little more complicated than if I'm differentiating with respect, if the variable of differentiation is the same as the independent variable of my function. That's more convenient and simpler in a way, but sometimes we might need to do this. Okay, so let's get a little practice with this guy then. If z equals xy squared and I'm differentiating with respect to t, I just have to use the chain rule whenever necessary. Okay, so I'm doing x times the derivative of y squared. Well, the derivative of y squared has how many layers here? It's got 2, doesn't it? Because I've got the squared layer, and then I've got the layer inside, which is different than my variable of differentiation. So that derivative is going to be something other than 1. So I need 2 layers there. Okay? So my derivative, the first layer is derivative of hand squared is 2 hand to the 1. The next layer is going to be times the derivative of y. What's the derivative of y? It's not 1 this time because I'm not differentiating with respect to y. It's just dy dt. Okay? See what I'm saying? That derivative doesn't just disappear because of this. This whole part right here is, so let's label these things a little bit. Let's say that that's u and that's v. This is u times v prime. Right? No, we're not done yet. You're right. Now we got to keep going. So we did u v prime. No. Now we got to finish that was just the chain rule that we needed to calculate v prime. Now we got to go back and finish the product rule. So now we've got v, which is y squared times the derivative of u. So there's v. What's u prime going to be? What's the derivative of x? Dx dt, because we're differentiating with respect to t, exactly. So one thing we want to probably be concentrate on doing now that we haven't had to do in the past, we've always gotten lazy and just said, the derivative of u, like in this case, we would have said y squared times the derivative of x. We can't just say that anymore. I just did to you guys, but what should I say instead? I should say the derivative of x with respect to t, right? In the past, we've never done that because when we've dealt with problems like this, we've just said, well, what's the derivative of x squared? Well, it's 2x. But really what we meant was, what's the derivative of x squared with respect to x? And that's equal to 2x, right? Because these have always matched up, we've never really had a need of specifying what we're differentiating with respect to, but we need to start doing that because we're not going to constrain ourselves to only problems like that anymore. So up here, notice I said it differently. We said, what's the derivative? We have x, derivative of x squared is 2x times the derivative of x with respect to t, which is dx dt. It's not just 1, okay? So that's our answer. It looks ugly. It looks ugly, right? We've got these extra derivative terms in there that now we're stuck with because we're differentiating with respect to this other variable, t, instead of just x, right? Okay, so we'll come back to all that. Let's warm up with something like this. Find the tangent line when x equals 3. Well, what do I do? Tell me again. To find a tangent line, what do I need? I need a point. Okay, well, let's get a point. What's my point going to be? So my point of tangency, I'm plugging 3 in, and what do I get back for my y value? 9. There we go. Everybody see where we got that? Okay, just plug it into the function. We haven't done any calculus yet. Now we need some calculus, though. What else do we need for a line? We need a slope, yeah. We need a slope of the tangent line, which is the derivative evaluated at what? 3. Okay, well, we better calculate the derivative, huh? What is y prime? 2x. Now, because we're differentiating with respect to x, how many layers is this? One, right? Just a plain old simple one layer function. So we get 2x, and f prime of 3 then is just going to be 6. Agreed? Okay, so then we plug this stuff into point slope, and we get y minus 9 equals 6 times the quantity x minus 3. And what's that give us? 6x minus 18 plus 9. 6x minus 9. Everybody agree? Okay, and we know what that looks like. It looks like that, right? There's our tangent line right there. Okay. Does that move? No, I guess it doesn't. Okay, so how about this one? That's different. That's different than anything you've ever seen, right? All the functions we've dealt with in the past, which we've differentiated, have always been explicit. Why? We've been differentiating some dependent variable with respect to an independent variable, where the dependent variable, the function variable, is isolated. Okay, it's by itself to the first power. That's different. Y is not isolated there. Y is being squared. So what do we have to do now? Okay, we could take the square root, couldn't we? Okay, that's one thing we could do. So we could solve if I square root both sides, what would I get? I'm going to twist this around. So we have x equals y squared. Oh, no, I won't. Never mind, I'm not going to do that. Y equals x squared. So if I square root both sides, what do I get?
It's y squared equals x.
Oh, I wrote that backwards, didn't I? Yeah. So what do I get?
Y equals plus or minus.
Plus or minus. Yeah, right. Plus or minus. I've got y equals plus or minus. So if I just look at the top, that's what it looks like, doesn't it? Okay. And it'd be pretty easy to do this problem now. I mean, this would be no harder than the previous one. When x is 9, if I plug that in, if I plug in 9 to this function, if I just take the positive one, let's make that red. Oh my goodness. What was that? There we go. If I plug in 9, I get back 3, right? So there's my ordered pair. And all I'd have to do is just differentiate this function, calculate y prime, and plug in 9, and I'd get the slope of the function. We can do that, right? What's y prime? Okay, so that's the same as 1 over 2 times the square root of x, right? So I'm going to get 1/6, aren't I, for my slope then? So at x equals 9, m equals 1/6. And so we would just get this line, y minus 3 equals 1/6 times x minus 9, right? And I could put that in fancy slope-intercept form if I want to, but it's just going to look like that. There's my tangent line. Okay, but there's a problem, because there are two different solutions to this thing. If I square root both sides, I get y equals positive the square root of x, or y equals negative the square root of x. So I'd have to do all that similar work for this function also, wouldn't I? So what's that going to give me for a point? Well, if I plug in 9, I'm going to get minus 3. So I get this other ordered pair down here, right? Because there's two ordered pairs that have an x coordinate of 9, right? Because this is a non-function. It violates the vertical line test, doesn't it? Right? I could differentiate. Well, if I differentiate this, aren't I just going to get y prime equals negative 1/2 x to the minus 1/2? So negative 1 over 2 times the square root of x, which is going to give me negative 1/6. So So I get negative 1/6, and I plug all that stuff in, and I would get y minus negative 3. So y plus 3 equals negative 1/6 times x minus 9. I get two lines, and that's this other tangent line right there. Okay? Make sense? Okay. So, well, I mean, we just did this explicit process. Okay, the explicit process was we had to do this in two pieces, right? This is the one where, just for notes, I guess, we had y equals positive square root of x or y equals negative square root of x. So we got y prime equals 1 over 2 times the square root of x. And we ended up with the 0.93 m equals 1/6. And so we got the line y minus 3 equals 1/6 times the quantity x minus 9. Let's go ahead and put that into slope-intercept form. Let's finish the deal here. If I distribute that, what am I going to get? Okay. Minus 3 halves plus 3 is going to be plus 3 halves. Okay. So is that right? Double check me on that. Does that all make sense? Okay. So there's one line. Same process over here. We said y prime equals negative 1 over 2 times the square root of x. So we get the 0.9, negative 3. Slope of the tangent line is equal to negative 1/6. And if we plug all that stuff in, we get y minus negative 3, which is y plus 3, equals negative 1/6 x minus 9. Okay, if I distribute the negative 1/6, I'm going to get negative 1/6 x plus 3 halves minus 3 is going to be minus 3 halves. Okay. Does it seem just intuitively, does it make sense to you that these ought to be symmetrical? That the slopes ought to be opposites in this case and the y-intercepts ought to be opposites? I mean, given the symmetry of the situation, you just kind of know it's going to work out that way, and it does. Okay, so I'll point out one other thing here. I always like to point out the wisdom of the math gods because they're pretty wise. So this is a non-function. We talked about this a couple years ago. When we have a non-function like this, if we solve for y, what did we do? Well, the math gods gave us two separate answers in an or statement, right? Our answer was plus or minus the square root of x. Why'd they do that? Well, because they gave us back individual pieces that are functions. So they're good that way, right? They split this into two separate pieces, each of which does pass the vertical line test, and taken separately, they are functions of x. Okay, so when you isolate y, behind the scenes, you're always doing that. When you get multiple pieces to a function and or statements, when you have a function that stacks up vertically, the math gods have just broken that into separate functional pieces. Okay, that's a lot of work, though, right? I mean, we did a lot of stuff there. Is there an easier way? Okay, and I'm gonna take a picture here, and I want you to see if you can find a pattern that makes this whole process much simpler. Okay. Look at your derivatives at y prime. Let's just look at that part. Do you see a way that I could make those look the same? Now, given that our starting place for the red section was y was defined as the square root of x, and for the green section, our starting place was y is defined as negative the square root of x. Okay, I'm going to give you a hint. Look at this hint here. We could take this statement right here, and multiplying by -1 would be the same as distributing that -1 to either the numerator or the denominator, right? Let's put it in the denominator, and let's attach it to that factor right there. So I end up with something like 1/2 times negative square root of x. Same thing, agreed? Everybody agree? I mean, that negative there, I could factor that out front if I want to, okay? Why is that better? What is that equal to? What's going on there? How could both of those be summarized in a single statement? Y prime, what's y prime equal to? Oh, what did I just do? My goodness. Okay, it's 1/2 times whatever I defined y as in that particular instance, right? For the first function, this is my y. Well, it shows up right there, okay? In the second instance, this is my y and it shows up right there. But y prime, if I just make that substitution, if I just reverse that substitution and change that negative square root of x back to a y, I get the same answer in both cases, right? I get the answer y prime equals 1/2y, don't I? Right? Everybody see that? That's pretty cool. And so that gives us a hint. That gives us a hint that we could do this a different way. We don't have to explicitly solve for y. Let's just differentiate with respect to x. Okay? So we're going to start here. We are going to differentiate with, thank you, with respect to x. And what does that leave us with? What's the derivative of y squared with respect to x? How many layers does that have? 2, right? Because I'm differentiating with respect to a different variable. Okay? So what's that give me? It gives me 2y times dy dx, right? Everybody agree? Aha. 2y times dy dx. How about on the other side if I differentiate with respect to x? What do I get? What's the derivative of x with respect to x? 1, right? That's an easy one. I'm differentiating with respect to that variable. So I just get 1. Okay, well, a shortcut way of writing dy dx would just be y prime. Okay, so one thing we're going to want to do with implicit differentiation is to make it look simpler on the paper. We're going to call that a y prime. You don't have to, but you'll agree it makes it a little simpler. Okay, we'll solve for y prime. What do you get? Wow, that's pretty easy, right? That says it all. If y prime is equal to 1/2y, we can get our tangent lines really easily, right? Because what are we saying here? We want to know when x is 9. Okay, well, when x is 9, what's y equal to? Plus or minus 3, right? Agreed? Because when we just substitute, so I get 2 x values. That's okay. I would just have to both those x values I know I'm going to get two tangent lines then, because when y is equal to 9, I get or when x equals 9, I get two separate y values. Okay, what does that give us for our tangent line then? So that gives us slopes of y prime is right. Y prime is 1 over 2y. Okay, so then if I can calculate what the value of y prime is for various values of x, I should be able to go back now and build those tangent lines with only having to do the calculus one time. Okay. So when x equals 9, what's the value of y prime? Y prime, well, we have to specify, right? Because when x equals 9, there's two different values of y, plus or minus 3. We have to specify which one are we talking about. Okay, there's two different places. So when x equals 9, y is equal to plus or minus 3. So we're going to get two different ordered pairs. We're going to get the ordered pair 9, 3 or 9, negative 3, right? If I'm talking about this guy, well, the slope is equal to what? The slope is equal to my derivative, y prime is 1 over 2y. So 1 over 2 times 3. Over here, my slope is equal to 1 over 2 times negative 3. But I already knew that. We already did all that work, right? But now it's just in place. There's only one derivative to take and evaluate. Okay, so that tells me all I need. Look, I've got a point and a slope. I've got a point and a slope. We're done. Throw them into algebra 1 stuff, point slope formula, and we're done. Right? See the advantage. Okay, it's not just an advantage. It's more than that. It's essential, because if I go back here a little bit, what about that function? Find y prime. You guys don't know how to differentiate log functions yet, but we'll know here like in a week. But I double dog dare you to solve that for y, because it can be done, but wow, that's tough. That would be really tough to solve that for y first and then differentiate. You're going to end up with an absolutely atrocious looking function to differentiate. And in many cases, you can't even do it. In many cases, you can't even explicitly solve and differentiate. The only way you can do it is to implicitly differentiate. There isn't even a way to do it. The math doesn't even work to do it the other way. So this isn't just a good idea making your life simple. This is sometimes the only way to do things. Okay, so let's practice this a little bit. What did I have going here? I can't remember. Okay, so the implicit process is differentiate both sides with respect to x from the beginning, and then the y primes will just pop out. Okay, so how about this one? Find y prime when x equals 1. What are our options? Well, you could solve for y and get two separate functions that I differentiate individually, or way better, just implicitly differentiate with respect. Okay? So if I do that, what am I going to get? What's the derivative of x squared with respect to x? 2x. Plus, what's the derivative of y squared with respect to x? 2y times y prime, right? Two layers, because I'm differentiating with respect to x. You're starting to probably go, aha, I see a pattern here. Anytime I'm differentiating some variable other than x with respect to x, I'm going to get a prime popping out of that, right? And on the other side, what do I get? Derivative of 4 is 0. So all I have to do now is solve for y prime, and I'm done. well, I can divide by 2 and get rid of those. And so I just get y prime equals negative x over y. If I subtract the x and divide by y, and I'm done. Okay? All right. We'll keep going with this tomorrow. Now, tell me that's not cool. Isn't that cool stuff? You got to get kind of excited about that. That's